Hello, my name is Otávio. This is a video response for the video object-oriented versus functional programming. You are getting this wrong. What I want to illustrate here is that actually the video that I'm replying to is a very good video with a terrible example. Because the object-oriented solution, which actually is not very object-oriented, just an imperative solution, can only sum one type of container, one type of number. In that case, a primitive integer, a primitive array of integers. Where the final fold functional programming solution can sum any type of number in any type of container. So let's begin. I will start the presentation and hopefully everything is gonna make sense. Let's first do a quick recap of the presented solutions to sum a list of numbers. This is the imperative solution. This is the Haskell recursive solution. And the third one is the Haskell base library sum function, or at least something close to the Haskell base library sum function. And the first thing that I really want to emphasize is that this is really like comparing apples to bananas. Compare a full generic solution that can sum any type of container and any type of number with a solution that can only work for one type of container and one type of number is unfair. So I want to level the playing field. And I'm going to do that by generifying the Java solution as well. But first, let's go back to the first presented solution. And I want to show that explain to someone that never coded or has little experience with coding is not that trivial. You have to explain variable assignments. You have to explain what is a for each loop. You have to go and show each step for the person to realize why total would have 6 in the end of this execution. It's not the most trivial thing. The Haskell solution is not trivial for someone that never coded as well. But you have actually less things to explain. You have to explain that for an empty list, you return 0. For a not empty list, you return the sum of the first element of the list plus the function sum applied for the rest of the list. While this still might be confusing, if you look for how we decompose the step by step, you don't have to deal with iterations, you don't have to deal with variable assignments and things like that. You're actually just replacing the commas by add signs, and this is to show step by step why this will sum 6. So it's just a matter of preference, I think. Let's start generifying the Java solution then. So if I want to sum an array of doubles, what I do? Okay, I just replace the word int for double, copy this thing and create a method overload. And yeah, do this for every single type of number I want to add. For something that's not primitive, the syntax is a little bit different. If I have something that's not an array, I will just, overload this method again. And this will just keep piling up and piling up and piling up. And it's completely ugly and impractical. Imagine the number of combinations that this can wield. So we have to find some better alternative. Generifying the number containers itself is quite easy, and we can rely on the old object orientation for that. You see the hierarchy of the Java collection, that every collection actually extends from iterable. And what iterable means means that the collection can give you a way to go over each of its elements. So we can replace here the method parameter to be iterable, and then we don't care if the hash set, a array list, a linked list, any type of list, any kind of set, is a queue, whatever, or anything that you saw on the previous screen, it will just work. So here are some examples. this will sum everything here adds to 6, right? This a list of 1, 2, 3 adds to 6. Uh, a array list adds to 6. A set adds to 6. For the the array of primitives is a little bit different because it actually doesn't extend from collection, but you can easily, with little code, provide an iterator for it, and then yeah, the sum will just work. Like even for a map, like if you have a map, if you get the values itself are iterable and they will sum to 6. So this kind of solved for containers. But what about the sum of all type of numbers? And this is a little bit more complex. This is the number class definition in Java. Most of the classes that represents a number will extend from this class. But this class is not very useful to us because a number is just something that has a value and can be converted to a primitive type. And it does not define any type of arithmetic operations. So even I convert my old code to be an interval number, uh, I don't know for what type I should use, what type I should convert the number in order to do the sum. And also, even if I convert everything to a double, I still might lose precision with longs, big decimals, etc. So let's try to use object orientation to solve this problem. This is an interface summable of the type T. T can be anything, it doesn't matter. But for the methods that I have on this interface, if I call 0, it must return a summable of the same type I'm defining. The method add must receive a summable of the same same type I'm defining and return a summable of the same type I'm defining. And finally, get value should give me the value that the instance of this interface is actually wrapping. So let's see a definition for that, and let's do it as a mutable class, the same way that numbers are usually defined in Java. This is a summable class definition for integer. So the value is an integer. It was your old type T, and you construct by passing integer. 0 will give you an integer summable of 0 with this auto box in here. Adding will basically construct you a new integer summable by calling the sum static method on the integer class. Basically, there is a sum definition on integer class, but it's not binded to any interface. And we're gonna use it to do the sum of this other summable and return you a new summable with the new value. And finally, get value that will just return you the value that this class is wrapping. Does it seem like a lot of work? Because for me it does. It's a crazy amount of work and it's really ugly. So let's change our code to use an interval of summable of t, where t can be anything that you expect to represent a number, but can truly be anything. Uh, the first thing you see here that I actually have to pass the 0. So the 0 method definition I did back then is kind of useless. And why I have to do that? Well, because if my interval doesn't have any number, how can I get 0 from an instance of summable if I don't have any instance? So I have to provide 0. So I might even remove 0 from the interface as well. Uh, so here I start the accumulator with 0, the total of 0, and then for its summable, I will apply the sum operation, which now is completely generic, and return the total, which I'm defining as a summable of t as well. So this example of this working. Let's say I have a list of numbers, a list of integers, and then I want to sum this list of integers passing to this my new generic sum method. So I will use the good old object orientation, and go through each element of this list and add it to a new list that's a list of summables of integer by basically wrapping it into an integer summable. Now I have a list of integer summables. Amazing. So let's call the sum again with your brand new summable list. Okay, now probably you're thinking, I should have just duplicated code. All these efforts not worth it. Or maybe you're thinking, is there a better way? And I truly think there is. But to do that, we have to slowly move this code toward functional programming, toward a functional programming paradigm. Uh, so let's do the first transformation. The first thing to notice is that I'm not converting my type t anymore. Now I receive an interval of t and a zero of the type t, but I also receive an extra parameter, a function that maps this type t to a summable of t, which I call toSummable. Let's see how this works. So I will initialize my total by applying this function to 0. Now I have a summable of my type of t, that's 0. And then for each number t, I'll add to this total, which is a summable, right? Making each number also a summable. And then I have my total. I think here it illustrates quite well how this works. So I have a list of 1, 2, 3, and my number is 0. And the lambda function that I'm providing to do the transformation is the constructor itself of the summable class T. So yeah, I already cut a lot of code. Now we can just call like this and don't do any conversion, right? But this can be even better because in reality, wrapping a type T is quite useless for a problem. Wrapping a number is quite useless for a problem. If we model this as just pure functions, we can save us a lot of boilerplate code. So now I'm defining a new summable interface. So we can full stop wrapping a value and define just pure functions. Adding is just adding two numbers, 0, returning 0. What this means that like you don't have a number that's summable. You have the behavior that give that number the property of being summable. It's a little bit different because now you can have a single instance to your whole system, and because again this is completely stateless, and you can just pass this single instance along. Let's write once again our sum function. You don't have to pass the 0 anymore. You just have to pass a summable instance that's the same type of your interval t. And now we can actually use the zero function because it's not the situation that you can have an empty interval and you don't have a summable instance. Now you have a single summable instance that you can use to get your 0. So now the zero is useful. And again, now it's a little bit different. You are adding two numbers, but still you're not wrapping the number, right? You're just applying a function. You're not constructing a number just that you can add them together. You are just applying a function, and you keep applying this function till you have the total, and you call it like this, right? You send your interval of numbers and the instance of summable for the type you want to sum. Finally, here it is, the code. You probably already noticed that this is very similar to the sum function that we are trying to generify. Start with a value, apply a function to each value of the container uh, with the current value of the accumulator, and finally returns the accumulator, right? So if this function is a sum, And if this base value is a 0, there you go. Then you have the sum function. But this works for several things more. It's a very generic concept, a very basic concept of functional programming. That because of functional programming, actually, you don't have like accumulator. You don't have something. You don't have like a side effect because this for is a block of side effect. And it is produce a side effect outside of the scope of it. Mutate a variable. So this fold is an imperative version of the fold. It's still pure from the point of view of the caller. Uh, so there's no mutation outside of it, and there's no side effect outside of it. Uh, but still, it's a little bit strange to see like this. But considering that its iterable is also the iterator of iterable is also mutable, to actually represent it with recursion is even worse because every time you call next on your iterator, uh, you produce a side effect. Uh, now that we finally have a fold function, we can see that this solution looks really close to the Haskell solution. You have your numbers. You use the summable instance that give the behavior of the type t to be summable to get the 0 and to get the function add. And yeah, sum is just a special case of fold. Here, example of calling the function sum. Again, it's the same thing you saw before. But there's one thing, right? Java is not very friendly with this kind of approach. This kind of approach is really great to generify classes that you don't have access to, or just want to group these behaviors in a way that you can reuse and in a way that makes sense for them to be together. But probably in the case of summable, uh, I would just call fold directly, unless I had a very good reason to actually model summable like this. Uh, and yeah, just call fold and define the summable behavior on the fly by passing 0, by passing a function to sum. And there we go. That's basically this is the same of this. Here I'm just reusing here's an existing function. Here I'm defining a function on the fly. Uh, and one thing that you might not have noticed from the previous example is that the accumulator doesn't have to be the same type as well. This actually gives you a lot of flexibility. For example, here I'm summing a list of atomic integers, but I'm not accumulating to atomic integer because I don't want my result to be synchronized and have this performance penalty. But this actually extends for everything. I mean, you can fold a list back into a list. With that, you can implement map, filter, and this kind of functions as well. Fold is very powerful. In Java, there's the strings API, which gives you some of functional programming functionalities like fold, flat map, filter. And with that strings APIs, there are several ways that you can perform a sum of numbers, but only for in terms of the primitive types and not all the primitive types. And one implementation for each of those types it supports. So it goes on forever. It's like you have 1,000 sums in Java. The good news is that Java actually has a built-in fold function in terms of the string API. And this one is truly generic. It works for any kind of type, and it's called reduce. Reduces fold. You can see I can sum a list of integers, or I can sum a list of big decimals. Not they are not primitive types, but I still can sum them. With almost all types of containers in Java being able to easily be turned into a string, why reinventing the wheel and not just use the provided fold? Since the beginning, you have been folding all along. Since the first solution, it's already very similar to a fold. It was just not generic. But now, what about making the recursive Haskell solution generic as well? Dun, 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 dun. And I can do it in one slide. So the first block, just a recap of the solution, the recursive solution. Uh, but then you probably realize that, oh yeah, this really looks like a fold. So why not just make a requirement that the container is foldable? And there is one interesting thing, like foldable, for a container to be foldable is like for a Java collection to be iterable, right? I mean, it's really expected that a container is foldable. So you can write in terms of saying that your container is foldable. Then you have a foldable of int, and then you go to a int, right? That's the kind of a function signature. Uh, and then basically you can write the function like this. Fold, and X to a fold right. Uh, there's this recursion leads to a fold right. Not getting into details, but yeah. And adding, so basically the function that you define in Java, you can just pass this because not like Java add have a very special meaning. Like it's a special operator that operates on primitive types. Where in Haskell, add is just a function. It's just a function that is fixed by default, but nonetheless is just a function, and is fixed by default because it only has special characters. You can even omit the t, because if you just use fold right of plus and 0, you do a partial application, and then you have a function that expects a container of integers to be sent. So you don't even need to send the t. And when I say that something's foldable, I'm giving the examples of type class. The way I did with the Java solution. Basically, when I have a single instance of a single definition of a foldable of that container, and I pass the single instance along, the same way I did with Java, but with one big difference. Since we're not talking about state, we are talking about only about giving the behavior, and it's completely stateless. I only need the affordable instance of my container to be in scope. I don't need to pass it around. I need it to be in scope. I need it to be imported. And basically, I need to declare that, hey, I want T to be foldable. This is a requirement of T. That there is someone that implement the behavior of foldable, the way we did with the summable type class in Java. But then you probably realize, okay, oh yeah, but how do I generify the number? How do I generify the integer itself? But then it becomes much more simple, because actually the plus is not a special syntax for primitives or anything. It's just a function, and it's a function of number. When you say that int is a number, it's because someone gives the behavior for the int to be a number. So I can add this as a requirement as well. So I have now the requirement that the container is foldable, and that my a is a number. I don't have to pass the instance of number. Don't have to pass the instance of foldable. I just need to have its definition on scope. And then you can do something like this, like your son is is the same thing, but I use the from integer, because basically numbers, to be a none, there's besides the plus, minus, and etc. There's also the definition that you need to be able to construct this number from an integer literal. So let's say you are summing doubles here. This from integer will build you a double containing 0, the representation of a double containing 0. The same way that I did like the zero on the Java type class to have the same type, to get the same type of the number I'm adding. This works, but this actually, one of the few syntax struggles in Haskell is that this from integer is implicit. If I just put 0 here, is 0 of whatever number, whatever none I am adding. So this actually works, and this actually works for anything for any container containing number, because almost any container, because almost any container will be foldable, and it makes sense for something to be called a number if there's the behavior of the number, regardless of the data I'm representing. So just some examples of this working for integers, for floating point, for fractional numbers, rational numbers, from a set, from the type of collection, from an option, and which also nothing will to zero. So here is some methods of the non-type class definition, right? Like you have your plus, your minus, the from integer that I mentioned, and some other methods. I didn't put everything here. So and also I added here a little bit of the description of this from integer, the syntax sugar that I showed before. And it's why that the sum actually works for any number, because being a number means that you have some properties, and one of the properties that you can add, and adding is just a function that takes a number, another number, and returns you a number, and all of the same type. We have 8+ instances of none in the Haskell standard library. This means that almost anything that can be interpreted as number will have an instance of number. So yeah, your generic sum will work for almost any type of container and almost any type of number. And yeah, everything is a number. Being a number means, or none, means to have an instance of none. Everything is just functions. So adding to numbers is just infixed by default, meaning because it's a function with only special characters. But you can call, as you call the other functions in Haskell as well, by putting parentheses. So this is the same as this. So 1 plus 2 is the same as of calling the plus function and and passing the two parameters 1 and 2, which is the same of this, because actually equals is also not a special operator at all. It's just a function. And then this is the same as this, and that's the same as this. I hope it's clear. So, as a little conclusion, is that Java have several sums that only cover primitive types. Haskell just needs one for everything. And while fold is a very basic construct, you don't need to understand it to make a sum, because you have a sum method that just works. You don't need to pick inside of it. That's why I think that the Haskell solution is even simpler than the Java, not just because fold is a really way to generify this, but because you can actually just apply, and it probably just work for the container you have if this container have numbers inside. And a takeaway is that the best way for doing a generic sum, even in Java, is using FB, is using a fold, is generifying with functional programming. Because when we did it with object orientation, it was too much syntax, it was really ugly, it had too much instance creations and everything. And when you go and walks towards a functional approach, it just simplify things. And another observation is that this fold that I did here in Haskell is not the way it's in the standard library. The two implementation is actually on the foldable type class itself. It's based on fold map, reinforcing the monoid properties of the operation. I'm not going to get into details because then it's a whole other video, but it's close enough. And finally, I rest my case. Hopefully, you find this video useful. I didn't want to offend anyone, and I didn't want to bash on the other video. So it was just a small part that I disagree, but I think it was worth enough to give my own opinion, even though you might disagree with it as well. So, and that's all right. Doing this video, I also realized how hard it is to actually record a video, and so a lot of respect for the continuous delivery video, because it is a really well made video with, looks professional, and the guy speaks much better than I do. trying to bring another point of view to the conversation. That's just it. Thank you for watching, and hopefully I'll see you guys soon, or not, because yeah, it's hard to do videos. Take care. Bye bye.